group reporter for group 3, and I'll be going over the Rankine cycle. So quick outline. First I'm going to do a quick little theory recap and then go through some of the results, and then talk about the uncertainty and error. And before I begin my presentation, I want to preface with the fact that the Rankine cycler is broken, and so before we even got to steady state, we lost all of the water. So our data is a little messed up, and I don't have all the data needed for all the results. So just to recap, water is pumped into the boiler where it's converted into a high energy steam, where it flows through the turbine, where it spins the turbine, and that energy is then generated through the generator. Then it goes through the condenser where heat is rejected and it's condensed back down to a liquid, and then the whole cycle starts again. The Rankine cycler that we have in the lab doesn't have a pump, so you just fill the boiler with water and then collect the water in the condenser. Here are the results of the boiler temperature versus time. The little triangles where steady state begins and the little squares where steady state ends. Like I said, we were not at steady state technically yet with this data, so that's just kind of going off the data that we get. We're trying to achieve steady state before that, so we've gotten there, we just didn't know it yet. But as we notice, the boiler temperature is just constantly increasing. And then here's the fuel flow versus time. So this is the fuel flow into the boiler to heat up the water. You can see exactly where it cuts off and just drops off, and the same time markers. And then, like I said, we were trying to achieve that steady state. So to do that, we had to slowly open the steam admission valve to let the steam begin to flow through the system. And so that's why you have a little dip in the beginning where we're trying to maintain 110 psi. As you can see, we kind of level out towards that around 109 psi, so not too bad. And then it also dips at the end when the machine cut off. Here's the turbine inlet and outlet pressures versus time. The pressure when the steam enters the turbine is a much higher energy steam. That's why your PSI is much higher, and it's a little bit more chaotic than the continuous lower pressure at the exit. And then the turbine inlet and outlet temperature, once again, constantly increasing, kind of like how it was with the boiler temperature, because it is the steam flowing from the boiler. And you can see again that it kind of started off a little rocky. That's because we're messing with that steam admission valve to let the steam begin to flow. Here are the amps that were generated by the turbine spinning. It's around 0.3 amps once we got to steady state. As I keep mentioning, we had to achieve that steady state, so that's why you have a growth and then a dip. And lastly, the voltage versus the time. The voltage at steady state was around 6 volts, which is enough to power a flashlight, stuff like that. So if you think about it, a small Rankine cycle like the one that we have in the lab is able to power a flashlight, so imagine what a giant one could power. And this is the turbine RPM, so the rotations per minute that we're going because of the steam flow. It's around 1500 when we choose steady state. Here are some results of states at a specific time mark. So it was at 90,950 seconds, but our data started recording at 90,000-ish seconds, so this is only about 1,000 seconds in. And like I said, we were kind of able to maintain that boiler pressure around 110 psi, so not too bad. And then here's in the boiler, how to find the heat added into the boiler. So you take the state value at 3 and subtract the enthalpy at 2. To find that, you do have to do a bunch of double interpolations between the temperature of 172, so between 150 and 200, and then between your pressures of 100 and 200, and how to do that for all of the enthalpies. But once you find it, you get it's about 2397 kilojoules per kilogram. And then the same process works for the generator, for the turbine generator, except when you're looking for the work rate, you multiply that by the mass flow rate. That is something that I do not have because we don't have the volume that was consumed by the boiler because it was lost to the floor. And then the efficiency would be the power by the generator over the power of the turbine, which would be this right here. And the work of the turbine was about 45 kilojoules per kilogram. And same thing for the condenser. Use your enthalpies to find your heat rejected, which was about 2352 kilojoules per kilogram. And then to find the mass flow rate, you use the specific volume in the boiler, which is about 0.27632, and then divide that by the volume of water consumed by the boiler, and then you would divide that by the steady state flow time, which was only a minute and about, 40 seconds. Here are some state data, so just at different locations, the pressure, temperature, volume, enthalpy, internal energy, and entropy, just at different states. You might notice the turbine outlet is equal to condenser inlet, and the condenser outlet is also equal to atmospheric because it was being expelled to the atmosphere. These are some assumptions that we had to make when doing calculations. And then the thermal efficiency is the work of the cycle over the heat added. So because there was no pump in the cycle, it's just the work of the turbine over the heat added, which is about 1.8%, which is a really low efficiency, but it kind of matches what one of the other sections got with 1.7% efficiency. And then lastly, there's a lot of room for uncertainty and error in this experiment because you have digital resolution, so it's to one of the significant digit. It was a very short time period, so we didn't really have that many samples in our data. Didn't account for heat or pressure loss between condenser and boiler or any flow through the pipes. And then there's a lot of error because there was significant boiler leakage, and we had to do those manual adjustments to maintain steady state. In conclusion, the Rankine cycler in the lab is broken, and the data, however, confirms that there was higher energy steam in the boiler and higher energy in the turbine than in the condenser, and that the cycle worked as we expected it to, and the experimental run of the Rankine cycle had a very low thermal efficiency. And then here are my citations, and that is all.
Thank you.